Here's problem 1322. An object is released from rest at a distance h above the surface of a planet, mass big M, radius big R. With what speed will the object strike the surface of the planet? Disregard any dissipative effects of the atmosphere of the planet. Alright, so in our original situation we have a planet, and it's got a radius R, and we're going to drop an object that has an additional distance h above the surface of the planet. Let's call this object mass m, and of course the mass of the planet will be located at the center of mass. Let's call that big M. Alright, in this case where we have simply two objects that are attracted to each other, and one is not necessarily in orbit around the other, we simply just have two masses with a distance between them. They are bound by an energy, and the energy of binding is equal to negative G times one mass, big M, times the other mass, little m, over the distance between them, R, as a variable. In this case, our R is this full distance right here. So our little r is equal to the radius of the planet plus h. This is the way things look like initially. But then the object falls, and it's going to hit the planet. So we have this situation right here where the mass, little m, hits the planet. And at this point, it's still a radius r away from the planet. So our big M and little m are still separated by a distance of the radius of the planet. But little m now has gained some kinetic energy, so it's got a final velocity when it hits. So the energy in this case, our final energy, is going to equal 1/2 mv squared plus our potential binding energy, which would be negative G big M little m over the distance between them, which in this case would just be the radius of the planet R. Okay, and this is the way things look like finally. Alright, it should be true that our initial energy should equal our final energy. So we should have that a negative G M little m over our original distance, which is R plus H, that energy, total energy, should equal 1/2 little mass times velocity squared plus the binding energy, negative G big M little m, over our new distance of R. The initial energy equals the final energy. Let's divide both sides by little m, get rid of that. Solve this for velocity. So we have 1/2 velocity squared is going to equal negative G big M over big R plus H plus G big M over R. So we would have that the velocity squared is going to equal G big M over over 1 times 2 times 1 over R minus 1 over R plus H. I want to find a common denominator for my two fractions. So this is going to equal 2gm, and then multiplying 1 over R by R plus H over R plus H, I'll have R plus H over R times R plus H, minus, and then I'll multiply the second fraction by R over R, so I'm going to get R over R times R plus H. Alright, so now I have a common denominator. In the numerator, I'm going to have R plus H minus R, so the R's will cancel there. And now this will be equal to 2gm, and it'll be H over R times R plus H. Or I would say that my velocity is the square root of all that. So 2gm h over r times r plus h square root. Alright. Now let's take a look at this. Normally, if we were in a situation where we were close to the Earth and we fell some height h to the Earth, in the past we have said, well, that velocity, when you start from rest and you fall to the Earth, that velocity is equal to 2gh square root. And g is actually the gravitational acceleration of the Earth, so if that were g times the mass of the planet over the radius of the planet squared, if I put that into this equation, then I would say that my velocity is equal to 2 times g times the mass of the planet times h over the radius of the planet squared, all that, square root. Well, in this result, we got, instead, that the velocity is equal to 2gmh over the radius times the radius plus h, all that, square root. So there's not a whole lot of difference. The difference here is that we've replaced, more accurately, r plus h for one of the r's originally in our approximation before. And this is because gravity is changing in value as we're falling this distance h. Before, we just assumed gravity was constant over our whole fall from distance h, and now it's changing in value, so we come up with this new equation, which is very similar but more accurate for determining the velocity as we hit the Earth or hit the surface of the planet.